Bien, muy buenos días entonces con todos. Es un placer tenerlos aquí. Good night, Dr. Ram-Singh, to have your participation in our REUMATPERU 2022. Vamos a presentar al Dr. Ram-Singh. We are going to introduce Dr. Ram-Singh for all the people who is now here, please. Wait a minute. Voy a compartir algo de la historia del Dr. Ram-Singh. El Dr. Ram-Singh tiene un doctorado en matemática de la Universidad de Ambercard, Agra, India. Es también magíster del Departamento de Matemática de la Universidad de Jammu y bachiller también en la misma universidad, bachiller de primera división. Tiene habilidades técnicas, utiliza MATLAB y R, el software R. Y sus áreas de interés son la biología matemática, en primer lugar, los sistemas dinámicos, la dinámica evolucionaria y la matemática epidemiológica. También la dinámica poblacional y la ecología teórica. Algunas de las publicaciones que he seleccionado aquí son las dos últimas que él tiene, y como ustedes podrán apreciar, tiene que ver con epidemiología matemática en la malaria y también con la ecología matemática. Algunas pasiones de las cuales compartimos con él, y algo muy particular que tiene el Dr. Ram-Singh es que él es miembro externo de nuestro grupo de investigación Ciencias Matemáticas para Ciencias de la Vida de la Universidad Nacional Mayor de San Marcos, Facultad de Ciencias Matemáticas. Es por eso que para nosotros es todo un placer el poderlo presentar el día de hoy y que nos comparta algunas de las cosas que está haciendo y que sirva de motivación no solamente para los miembros del grupo de investigación, sino para todo el público aquí presente, tanto a nivel nacional como a nivel internacional en términos de Latinoamérica, que también veo que están presentes el día de hoy. Así que es un placer el tenerlo aquí y vamos a decirle al doctor Ram-Singh que puede ya, él está muy entusiasmado y muy triste porque no pudo la semana pasada, pero parece que esta semana viene con todas las ganas de mostrarnos qué es lo que está haciendo. Okay, Dr. Ram-Singh, it's your turn. Please begin with your talk. Thank you very much.
Thank you, Professor Roxana and other participants, Professor Lourdes Vasquez and other participants.
It's okay.
Actually, first of all, I apologize because my talk was scheduled later on the 4th of November, but unfortunately, because of my ill health, I could not available at that time. And thank you, Professor Roxana, for understanding. And you took care of a lot of me that your health is first priority, then you can deliver the talk at some other times. So thank you. Now I am okay and available to deliver the talk. So here's a good morning to all of you, because there is a good morning and here's a good night, but there is a lot of different time zone difference here. Professor Roxana, are your participants comfortable in English? Okay. Am I listening?
It's okay. It's okay. It's okay. Everybody is going to understand you.
That's perfect. That's perfect. So, so dear participants, good morning to all of you. So today I'm going to deliver my next talk. Earlier, I have also delivered one talk last year in the month of November. I still remember that. It was last year, and that was a very interesting talk. And in continuation to that, because I am a group member, also external group member of your group, which is performing very well in part of mathematical biology. So today I am come with some topics, that is some new aspects of modeling of cancer, HIV, TB, and diabetes co-infection. So I have chosen so many 3 or 4 diseases because I have done the modeling in such diseases, and some discuss the new aspects of modeling of cancers, HIV, TB, and diabetes infections. So first of all, so there is some preliminaries of my talk. I will discuss the modeling, analysis, and cure of cancer disease by X-ray therapy in the terms of mathematical modeling. This is the talk in which we will discuss about how the X-ray therapy can be helpful in using cure of the cancer but the concept is used in the terms of mathematical modeling. Second, the mathematical modeling, analysis, and applicable control to the infection of HIV, AIDS, and TB co-infection disease in homogeneous population. And another is we have discussed the methods which have you used to solve these models. That is, we have used a non-standard finite difference scheme for diabetes mellitus with TB and HIV co-infection epidemic model. And the last, there are some references work which is very important, because the work which we have cited, the work we have used in context to these references, this is very important. In the later stage, I will show you all the references work. So as Professor Aksana and its group is working a lot on the mathematical modeling, so it is just a definition, because you people are very well aware of the mathematical modeling definition. Anyhow, I am going to repeat it. The process of representing the behavior of real objects and the facts in mathematical language is called mathematical modeling. In fact, this mathematical modeling is a tool in study of the variety of diseases. Mathematical modeling is an important tool to study, to understanding what the population dynamics of a particular disease is happening. It's a very wonderful technique with the help of which we can understand and we can get an insight about the dynamics of the transmission dynamics of various diseases. The problem of endemic disease are a major threat to the human population, as we all of know that, because recently we have witnessed the havoc of the COVID-19. COVID-19 is still a challenge to many of the countries, European countries, American, South America, North America, then Asian countries. It has created a lot of terror among these population, and still this disease is present in the system. Although mathematical modeling has done a lot of work in this direction, but still the problem system present in the system. We have a lot of work on the COVID-19 also there. Compartmental modeling, this is a very important type of modeling which we often use in type of deterministic modeling. As we all of know that there are two types of modeling, stochastic modeling and the deterministic modeling. So compartmental modeling can be used in such type of population where we have a finite number of population. And this is deterministic modeling can be helpful when we have a certain discrete type of data is available with us. So in this modeling, we divide the entire population into various classes, which is known as a compartments, whereas each group represents a specific stage of epidemics. As we all of know that, because you people also work on a lot of the compartmental modeling. Depending upon the disease, various compartment divisions, but this is the most basic division into three categories. SIR are proposed, because this is a very simple and basic model as the SIR. Three compartments for the whole population are given, in which S stands for susceptible, I for infective, and R for recovered population, as we all of know that. So I am talking about the cancer modeling. So before actually come to the actual modeling, let us come to some statistical data about the cancer modeling as compared to in part of the Indian context. I have chosen a slide that in which, although the slide is not clear because I have chosen from the internet, it shows that all over the world population, 26% populations, they are suffering from the breast cancer, and 18.3% of the population, they are suffering from the cervical this type of cancer, and 6.7% of the population, they are suffering from the ovarian cancer, and 4.6 type of population, they are suffering from the oral cavity, and colorectal type of cancer, they are suffering from 3.7, and the larger part of population is suffering from other type of cancer, that is 40%. There are other type of cancers. This is basically main cancers which are really suffering the human populations. So if I talk about the Indian context, this is a data which I have collected from a organization which have made a survey that type of cancer in 2019, 2020, and 2021. The people who are suffering from the breast cancer, this is the population was 1,510, and the population which are suffering from the lung cancer in 2019, 353. Ovarian cancer, that is 211, and the lymphoma cancer, that is 257, and prostate cancer, that is 272. Similarly, in 2020 and 2021, the data is given as, and the total population is also given as. So this we have seen that every time the population is going to be increases, and this is a very large concern to all of us. And if I speak about the all over the world scenario, so this is a data which I have taken from that is the Asian countries. This is the data in the 2020, in the blue lines, and the red lines, they show that the data which is expected to be increased in 2040. I mean to say that in the next 20 years, the data will be reached to a very insignificantly changes in the numbers. For example, here in the Asia, the current data of the cancer patient, they are indicated by the blue lines. This is a this is 95 lakhs and 3,710 type of populations which are suffering from the cancer in the Asia, and in the 2040 the population expected to plus 59.2%. This is really very concerning data. In the European country, if we talk about, it is 21%. There we will expected to rise in the next 20 years. In Northern America, it's a 37.9 expected number of population which is expected to be suffering from this type of cancer in the next 20 years. And Latin America and Caribbean, African countries, and Oceanias. So this is a data. This is really data is very disappointing, because the population who are going to be suffering in the next 20 years, this data is very significant in numbers, right? So this is a very stage of very great concern. So let us come to the modeling techniques and expression which we generally use in form of mathematical modeling. Different kind of modeling is there. First is the differential equation. We generally do there. Differential equations are the equation that unknowns are function and they imply these functions, but they are also derivatives. In case of the dynamic system, ordered differential equation are used, and the independent variable or one in the respect to the derivation is performed is time, because this is a time dependent model. And for a dynamical system involving more than one independent variable, partial equations, they are also exploited, as we know that. And second kind of modeling which we have seek the help of computer, that is a neural network. Neural network is a computational science, is a network of artificial neurons or nodes. The nodes and their relationship are formed with the integration of the different algorithms that copy the way the brain operates. They identify the best network according to the provide input and output experimental data. Another kind of modeling, that is agent-based modeling. Agent-based modeling is a class of discrete mathematical and computational model that are able to represent the behavior, action, and interaction of different autonomous agents, and to highlight the whole system as the integration of its different actors. They differ from the rule-based model, especially because of their notation of space and incorporation of the micro environments. Another important kind of modeling, that is a neuro-fuzzy modeling. This is also very important modeling. We mostly use seek the help of this type of modeling. So neuro-fuzzy logic is a kind of polyvalent logic in which the values are ranged from 0 to 1, and that are not true and false. Neuro-fuzzy modeling are a hybrid combination of the neural network and fuzzy logics. Another kind of modeling, that is cellular automation. Cellular automation is a kind of discrete modeling composed of regions of a cell with different possible states. At each discrete step, a new generation of state is produced according to a set of rules based on the current cell and the state of the neighboring cell. So usually the operate rules are same for each cell except for stochastic cellular automations. When the operate times are different for various grid position, asynchronous cellular automation is preferred. So patterning net is another graphical discrete modeling technique in which the network nodes are not biological entities but condition and events. Directed interaction connect the different conditions going through one and several events on transition. And another kind of model, that is a cellular ports model. Computer cellular ports model are cell-based model that represent the component of cellular structure by using the principle of free energy minimization. So there are if I speak about the first thing, differential equation, we have seen that there are a variety of techniques which we can use in the formation of mathematical and computational modeling of cancer dynamics. So there are so kind of another techniques. Many people use these techniques with the help of computational work, because in this case we need a lot of computer information and high-level programming is needed in order to perform such kind of computing. Generally, we use this differential equation. This is the old structure technique, but neural network, agent-based modeling, neuro-fuzzy modeling, cellular automation, they are the latest technique which can be used with the help of some computer programming and computer expert, and computational modeling can be used. So let us come to some basic model, because starting 2 points. So these are the ODS system and SINGH model. As we all of know that this is one of the basic model to understand what is the modeling concept is that. This is the first basic model which every person who is beginner in the mathematical modeling can understand this model. So SIR model, we all of know that we don't discuss in detail because we all of aware that SIR, this is a very basic model. A is the transmission rate of infection between susceptible infection, and B is the recovery rate, right? And S is susceptible population, I is the infected, R is the recovered population. And this is a transition grammar basic SIR model. We all of aware the systems. We don't need much explanation. Second kind of so little bit advanced model from this model SIR, that is SIR and I. So this is again A is the transmission rate, B is the recovery rate, and C is the relapse rate. We have another term that is C, that is relapse rate, and minus R, this population again going to join the infected class, right? SIRI, right? So this is again kind of modeling. We know the solution is by using very basic and traditional techniques. So another model, that's a SEIR model. So this is SEIR model is susceptible, exposed, infected, and recovered classes there. So again, they did A is the transmission rate, recovery rate, C is the relapse rate, D is the incubation periods. Incubation period is the time which is time taken by the infected population to be between developing the disease from exposed to infected class. So let us come to the main point, that is the modeling of cancer. Cancer is one of the most common cause of death in the modern world. If we tell you as per the last year data, there is the expected 80 million deaths. They are caused by the this all over the world by this cancer disease. So and the coming years, more deaths are expected to be done by this thing, because this is spreading like a wildfire. And so many kind of new cancer diseases they are going to develop. Cancer is a basically disease. This is basically malignant growth of the that is the undivided cells. The cell they are basically separated, and they are undivision, uncontrolled growth of the cell, and they are infected cells, and this causes a cancer. So cancer is basically collection of the infected cells which cause infection to another neighboring cells. So it is by the year 2030, it is anticipated that over 30 million people will have contracted the disease in the some form. Some form means they may have ovarian cancer, they may have breast cancer, they may have some lip cancers, they may have some another kind of cancer. So, but expected that 13 million, over 13 million people, they are likely to be infected from this disease. So many advancements in the cancer therapy, such as chemotherapy, immunotherapy, radiotherapy, surgery, has been made and has been available as per the medical development and medical sciences develop. But still, the challenges before the people, because as we do more and more advancement in medicine science, more and more challenge in the form of disease there appear before us. If I talk about the COVID-19, nobody has ever thought that the COVID creates such a havoc in the last 2 years, which the entire world has witnessed a large kind of loss in terms of economy loss, in terms of living beings, in terms of livestock, and other kind of loss which we have all of us faced in terms of COVID-19. So the basic cancer model with the 3 compartmental is formulated with the help of these 3 differential equations. That A is the population. This is basically, this is the A is the population of affected cells, B is the population of tumor cells, C is the population of acquired chemotherapy. So basically, this is a population dynamics model we have constructed, where A is the basically population of the cell, B is the affected cell, and C is the basically chemotherapy. This is a model which we have formulated for in terms of chemotherapy, and where we have terms, interaction terms like the A, B upon H. This is a factor which we have considered, special factor which have constructed that as the V is increases, the whole term they are going to be, as V goes to infinity, this term goes to be 0. So we have chosen this term especially in terms of like that, because when the population of V goes to infinity, at a time t goes to infinity, the entire population, this factor will be 0. So again, mu is the death rate, and K is the basically coefficients, A is the interaction with the chemotherapy cells, and V is the rate. This is basically taken as a entire population like this. This is basically a diagram of the cancer cells. This is a growth of uncontrolled growth of the cell, right? Infection cells. So this is a particularly we have taken that picture that what is the cancer cell like that. This is basically I have taken a spherical in shape, and this is the center, and this is basically figures representing the cancer cells, one of the cell. So these are some notations which we have used. That is the population of effector cells. B is the population of tumor cell. C is the population who acquired chemotherapy. Ka defined the demise rate of the effector cells. P is the recruitment degree of high immune effector cell. R is basically growth rate of the tumors. And V is the tumor cell capacity. A represent the cancer cleanup parameter. G cancer cleanup half saturation. And S effector cell growth. M is effector cell activation degree. Mu is the natural death rate of the cell effectors. Kv represent the demise rate of tumor cell. And gamma is the concentration or decrease in chemotherapy drugs. And VC represent the demise rate of individuals who acquire chemotherapy, and H the stiffness of the coefficient. So I will discuss the mathematical part of this that model in the later stage, but before that I will go back to a little background of the HIV. So recently modeling of HIV/AIDS is that recently the human immunodeficiency virus infection, which can lead to acquired immunodeficiency syndrome, has become a life-threatening disease in both developed and developing nations. It is a severe disease which breaks down the human immune system and leaves the victim more vulnerable to infectious and neurological disorders. Human immunodeficiency virus are spread by human bodily fluids such as the waste milk, urine, tears, spit, blood, and other bodily fluids. A clinical sign for the stage of acquired immuno syndromes is a decrease in the number of these white blood cells. So these are some symptoms, and these are some signs which develop in a human body when they show a sign of HIV or AIDS infection. So if I talk about a global data about the HIV epidemic, it has seen that in 2021, so there is a basically data with in the total adults, 36 million people who are adults who are suffering from this disease like HIV, and 1.3 million people they are living with in acquiring in 2021, and people dying from HIV related disease in 2021, that is the 5,600,000 people are there. Women, 19.7 million people, they are people living with HIV in 2021. People acquiring HIV in 2021, that is 6 million people, and 24 million people they are suffering from this. Men, 69.9 million, and children, they are less than the age of 15 years, they are suffering from 1.5. So this is very dismay and disappointing data. And total population is 38.4 million people who are living with HIV in 20 and 21, and 1.5 million people who are acquiring HIV in 2021, and the people who are dying from the HIV related cause in 2021, the data is also in terms of 6 millions, right? So if we compare the person with AIDS and the cancer among person with HIV co-infection, so data is before two people, number of people, persons who are affected this population in 1980 to 2012 data. So the figure is like this, in the gold, then significantly going and increasing. And if we case of the cancer cells, the persons who are suffering with cancer and HIV, they are also sufficient in the figure data up to 2005. So several mathematical models for the host immune system has been developed in the recent time. The basic HIV and AIDS mathematical model with 4 compartmental is formulated as, this is a DW. In the form of W is the basically M basically population size, and A is the recruitment rate of susceptible, beta is the transmission rate, C is the rate of sexual partner, mu is the basically natural death rate in each of 4 state variables which if we have taken the constant, D is the death induced rate by HIV, and rho is the amount of people who are ineffective, and mu is the average incubation period, right? This is the population. Now let us come to the cancer model. These are the few previous model I have shown you just how these the transmission dynamics model are constructed in terms of HIV and cancer. Now come to the actual model, which is the title of the talk, that is cancer models, and how can this model can be cured by the using of X-ray signal system. So in time of this, we have taken the OD model, cancer cell diseases follows three kind of population is taken into consideration: A1, A2, and A3. A1 is the population of healthy cell. We have taken the cell into three types: healthy cell, and population of quasi-infected cell, and the population of cancer cell. So three kind of cell is there. First cell, there will be healthy cell, no infection is there. Second kind of cell, they are quasi. Quasi means half infected. Cell are half infected and half are healthy. And third kind of population, that is the cancerous cell. These are the dangerous cell. And delta is taken as a strength of the X-ray signal. When we throw the signal strength, X-ray signal strength on the cancerous cell, the intensity is the delta. And this delta basically play a very important role, and the value of delta, the intensity, will play a very important role in the destruction of the cancerous cell. In the later stage, when we show the numerical result, we have shown the particular value which is suitable for this model, that when we throw on the X-ray this cancer cells, so how many intensity of this, so that if the intensity of delta is increasing, it may cause harm to other cells, also healthy cells. But the size of this delta should be chosen in such a well way that it only destroy the cancer cell, not the healthy cells. So this is very important point to be noted. So ST basically mechanical factor that is used for the X-ray therapy, because when we use the X-ray machine to destroy the cancer cell, some mechanical concept is used. So in order to take care of that factor, I have chosen ST factor that we have taken as a time dependent, because time is a very important matter in this modeling. Because when we throw the X-ray modeling to the cancer cells, so time is very important. So that how much time we have to throw the modeling, this is important. How much the strength of the signal should be there, this is also important. And then the carrying capacity of the different kind of cell is given as a H2, H1, H2, H3. These are the carrying capacity. So what is the carrying capacity? We all of know that carrying capacity is basically carrying capacity of a system up to which it survives up to a particular population. Because we know that every system has a capacity to sustain something. For example, our Earth, nature, has also is a carrying capacity. It can also sustain a population up to a certain level. Beyond that level, it may not survive sustain to the population. For example, if we have a population food for 100 people, and we have a population more than 100 people, automatically the food will be depleted, because the carrying capacity is a very important concept in our natural phenomena and non-linear this kind of modeling. And another kind of that is a parameter which we will consider, that is the competition coefficient. Competition coefficient of healthy cell and competition coefficient of quasi-infected cell, and Y3 represent the competition among the cancer cell. Because there is a Lotka-Volter type of model we have considered, and there is a competitive kind of population among these three kind of population. Healthy cell, there is also competition for healthy cell for their survival of food, and in kind of quasi cell, there is also interaction. And for the last kind of cell, that is your cancer cell, there is also a competition between these cancer cells which are infecting one and another cell. So there are these kind of cells, they are also fighting with each other, and they are putting the competition in order to survive. So this is a transition diagram, A1, A2, A3, and these are some rates which we have taken into consideration. That is can be understood with the help of this equation. If we analyze these equations, we have find the rates that population is coming from this population, then Y2, Y1, X3, Y3, and so on. These are some rates in terms of some population dynamics, right? Three kind of population there. So in these sections, we have done a mathematical analysis of this system by using the theory of stability analysis. This is basically only system which we can use to solve this nonlinear system, because there is no hard and fast rule to solve the nonlinear system of equation except this system. Sometimes we use the computational help, but this is the analytical technique which can be used to find the behavior of the system about the equilibrium points. So equilibrium points we can find by using the derivative equal to 0 and find the position where systems remain stable. So first of all, we find the equilibrium points. So first of all, that is the disease-free equilibrium points, which can be computed by taking the right-hand side of the derivatives to 0. When we take the left-hand side of the equation 0, so it is A01, A21, and A31. This is a disease-free equilibrium point, and these values are computers, right? Then we have find the basic reproduction number or not. Basic reproduction number, we all know that it is basically secondary infection which is caused by the number of infection. Secondary infection, they are caused by the number of secondary infection due to one infected individual or one infected persons. So this is a next generation technique which is have used, which is given by the Batmores. Very important techniques which all the mathematical biology persons use. This technique is a threshold parameter which help us to identify that up to certain value the disease will persist in the system, and up to certain value the disease will die out. And when the value of R naught is equal to 1, there is a situation that is called the chaotic situation there. Then there is a bifurcation will be arises. There is another concept of chaos will be started at this point. But R is equal to not is equal to 1. This is a very difficult point to be calculated. After we also certain that when R is less than 1, the disease will be die out of the system. If R naught is greater than 1, the disease still persists in the system and become epidemic. But when R naught is equal to 1, then this is a very difficult point to calculate it. Because R naught is equal to 1, this situation where the bifurcation and another branching will be started. So R naught is the spectral radius of the variational matrix, that is F into V inverse. So VF is the basically that is the compartmental two matrices, one of the infection disease transfer and new infections. V naught is the basically transfer of new infection. So on multiplication and analysis is omitted here. R naught is computed and the value is given as like this. It is a square root of x2, x3 and 1 minus a naught upon h2. 1 minus, this is basically a product of two coupling terms, 1 upon a s square t, and other terms are also y2, y3, a1, a2 upon alpha 2 and s2 square. So there are some theorems which we have concluded, which have done derived from the derivation. Suppose the expression x3 minus delta is greater than 0 and all this inequality holds good, then the healthy cell, quasi-infected cell and cancer cell are the coexist. Otherwise, they cells did not coexist. This is a condition we have derived from our this stability analysis technique. Second theorem said that the dynamic system stable has a quasi-infected cell eradication periodic solution a star 1 t 0 if the expression alpha delta m is less than x1, z is satisfied. Otherwise, the system is the solution is non-periodic. And third is the dynamical system has a cancer cell eradication periodic solution if the certain condition hold good, that is alpha 2 delta m is less than x2 z. These are certain conditions we have put in the form of theorems, what have omitted the proof because they are very lengthy proof. If you are willing, I will share the proof in detail. I will share the research paper to Professor Roxana so that it may have, because the detailed proof are given in terms of theorems of these theorems. So stability analysis, in this section we present the stability as the equilibrium points. Suppose A1, A2 and 3 non-negative periodic solutions of model 7. In order to check the global stability of equilibrium point, let us construct the Lipton function. We know that we can check the global stability of the system with the help of Lipton functions. So we are about the Lipton function, how to construct that. There are certain condition with the help of which we can construct the Lipton function, and that this Lipton function should be negative definite and it should be in order to be a system to be global stable. So this is the Lipton system of the 7 which we have constructed, and this system is finite, negative finite. So suppose the condition 2 condition, these are hold good if this y1 less than y2, y2 less than y3, x1 minus alpha delta minus x1 upon sigma 1 is less than 0, x2 delta 2 and this delta minus x2 upon this sigma 2 is less than 0 and x3 is less than 0 and delta of z minus m is less than eta z are satisfied. Then the model 7 has a global asymptotically stable quasi-infected eradication periodic solution. So we have seen the global periodic solution in terms of two, that is false in the term of stability and other in terms of local stability and in terms of global stability. So two type of solution are given here, that is in terms of periodic solution. Another condition is also given that. So this is basically numerical simulation result. We have seen that the variation of healthy cell for different kind of growth cell of healthy cell. In the x-axis, we have seen the time. In the y-axis, we have taken the healthy cell, and x1 is the basically basically X1, basically we have taken the signal strength which we have seen that in the beginning, because where I have changed the notation here. X1 basically represent the signal strength, the delta which we have taken as speaking orders. If I change the signal strength 0, 1 to 0, 3 to 0, 5, so we have seen that as we increasing the signal strength, right, from 0 to 0, 1, so you have seen that the healthy cells, their population going and decreasing significantly. But when we increase the value of delta to 0.3 to 0.5, the population of the healthy cells decreases, right? But they are also decreases with the passage of time. So it has seen that healthy cell, as we increase the intensity of, this is a very interesting result, as we increase the intensity of the X-ray signals, the healthy cell, they are also going to be infected, and their population going on decreasing with the passage of time. It means that we must be particular, we must be careful while choosing the intensity delta of the X-ray intensity. If the intensity is increases, it may affect the healthy cells. If the intensity is less than up to chosen a certain value, it may not cause damage to the healthy cell. Otherwise, can along the side of cancer cell, healthy cell are also affected. There may be cause some side effect of the X-ray therapy. So X-ray therapy is a good. In fact, we have chosen the signal strength to a particular value. So we have seen that if the value where this value of signal strength goes on increasing, it also affects the healthy cells. So this value must be suitable as per the condition of the patient. If we increase the value, it may destroy the healthy cell. This is also a side effect of the X-ray therapies. Healthy cells, this is another population H1. It increases in the population in the beginning. It increases, but after certain times, it goes on decreases constantly with the passage of time. So it's another kind of factors. So for carrying capacity, so carrying capacity we have already shown in the that in the beginning. It is some kind of capacity of a system. So this is also a cell capacity, because a healthy cell can sustain to a certain kind of therapy to a limit point. Beyond that point, they cannot survive. So every cell has a capacity to undergo to certain therapy. After that, it may cause a damage to the healthy cell also. So this is another kind of model which we have used to find that co-dynamical model. A kind of this is susceptible. It's a TB infection, HIV infection. It is a basically vaccinated infection, and A is a basically HIV infection. So this is a co-dynamics model in which we have kind of taken the 5 kind of population will be there. This is a model which is a little bit complicated, where we have chosen this beta 1 and beta 1 prime T upon M plus T as a this factor we chosen, intentionally chosen because we have to reduce the value of this TB and HIV by after applying some kind of vaccination. So these factors are chosen into consideration by taking some consideration to mind. So this is a model. So Q0 is the basically recruitment rate, beta 1 and beta minus is the difference we have taken. Delta D is a basically death rate, and lambda is the rate at which the TB population is joining the susceptible population, and phi is the death rate of TB population, theta is the death rate of the HIV population, V is the basically vaccinated, and HIV is the AIDS population. And you know that after the AIDS, there is a death, so there is no class recovered to the S, T, H, and V. So because after AIDS, there is a possibility of death, so there is no additional classes added here. So this is some population which we have chosen for the in the formulation of the mathematical model: susceptible host population, TB infected population, HIV infected population, vaccinated population, and AIDS population. So these are some recruitment rates. That is a constant rate for the host population. Beta 1 is a TB infection rate. Beta 1 prime is the rate of infection TB population. But in that case, this is basically difference is there chosen because when the population vaccinated is there. Beta 2 is the infection rate. Beta prime infection is the TB population. M1 is the medial alert, and M will read in the HIV class. Beta is the population TB and recovered class, and basically delta is the full-blown AIDS, and alpha is the disease-induced death rate. host ratio is denoted by D, phi is the vaccination rate for host, and theta is the relapse rate for host. So this is a transition diagram which shows that how this population dynamics is going to be happens in our models, right? So this is some equilibrium analysis. Here 5 possible points of equilibrium are obtained here. Disease-free, that is first population when there is no disease, only one population is there, that is N. Other population are 0, their existence from parameter values, right? Then another is the infection-free equilibrium on HIV. Only one population there when there is a no TB is there. It is given by these values, which is computed by taking the right-hand side to 0 and some conditional computed here. Another is the infection-free equilibrium point, that is TB is there, that is given as here. This is some calculation we have done there. And when TB is there, then other population will be there, but TB population component will be 0. Then vaccination-free equilibrium there, when there is no vaccination, the model value is given as this. And these are the parametric values. Endemic coefficient, when all the factors will be considered into consideration, where N is there, T is there, HIV is there, V is there, A is there. So these are some values. Linear stability model. So the model for Jacobian matrix point, equilibrium point is given like this. We all know that how this Jacobian matrix is formulated, but this is also called the variation matrix. But we have chosen by using basically all the factors. This is F1, then partial derivative will be there. And this is the reproduction number of our HIV infection. They are computed there. So this is the basically numerical result, because this model is solved basically numerically. This model is difficult thing to solve, and we have chosen this model is a numerically in population. And the first is the rate as TB population, time, and lambda is taken as a lambda from 0 to 1, 0 to 5. And we have seen that the population of TB population going and decreases significantly, and up to reaches to time, because TB is a curable disease. Up to certain vaccination, it can be cured. HIV, this is also going and decreases up to certain values. For the value of N is equal to eta is equal to 100 and 150. This is alpha. When the AIDS, this is also going on decreases. There's a TB population. So this is a vaccination. Vaccination is 5, vaccination rate. Now come to the model, which is the basically diabetes mellitus, TB, and HIV co-infection. So this is two kind of model we have discussed here: linear kind of model and non-linear kind of model, where P is a basically diabetic population without complication, QT is the diabetic population with complication, diabetic population with a complication, ST is the diabetic population with complication, and mu sigma is the newborn rates of diabetic mellitus, and mu1 is the basically developing rates of the complicated diabetic individual. Mu2 is the developing rate of infection with complicated diabetic individual. Mu3 is the developing rate of HIV complicated diabetic individual. Eta is the complication rate in diabetes, and eta2 are the complication rate which are cured. So this is the basically linear model, and D is the natural death rate of diabetic individual without complication. D2 is the natural death rate of diabetic individual with complication. So D3 is the natural death rate of diabetic individual with complication, and D4 is a natural death rate of diabetic population with complication and HIV. So this model is although complicated, but this is a linear model. The flow chart diagram is given as this. So we have find the critical values, that is equilibrium points. This is very easy to find there. In here, we have used the non-standard finite difference scheme technique to solve this model. So non-finite difference scheme is a very good technique to find the approximate solution. In this technique, we approximate the partial derivatives, right, to up to the certain differences at a particular nodes. What we do here, we discretize the entire continuous system into discretized forms. Then we form the discrete system into the form of some linear algebraic equation, and that solution of that linear algebraic solution will be converted to that our discrete system. So this is another kind of system that is called non-finite fundamental. We have discrete our entire 4 population into this at different nodes, j plus 1, pj, and these are the 4 equations. I rewrite the equation 15. Again, we have chosen this transition surface. So critical value of system given as this, we have find the critical values on solving system 7. just as a linear set of equation, we can solve it with recursive methods. We have find the critical values. So linear stable model, this discuss the system as expressed as this. We have find a variation matrix. We find all the values, and this is basically we have used the SOR methods. SOR method, successive operational relaxation method, to solve this linear system of equation, right? With the relaxation parameter omega as a from 0 and 0.0 and 1. And this is the characteristic equation. We have find that, and we find the lambda, and this is the eigenvalues, right? So G1, G2, G3, and G4. Let us come to the roots of equation 90 satisfy that lambda is less than 1 for all i's 1, 2, 3 if the following 5 condition holds good, because the system will be stable if all the these eigenvalues have the negative real parts, and only possible when this G1 is less than greater than 0, 1 plus G2 plus G3 plus G4 greater than 0, 1 minus G2 plus G3 minus G4 is greater than 0, 3 plus G2 minus G3 plus 3 times G4 is greater than 0, 1 plus G2 into G4 minus G3 minus G4 square is greater than 0. The critical solution is local asymptotically stable if all the eigenvalues have less than 1 for I from 1 to 3, 4. Otherwise, they are the unstable. So now come to the nonlinear parts. It's a model which we have seen that P12, this is the model omega. This is a nonlinear model. So what is the difference between the previous model and this model? Here we have taken the non-interaction terms. This model is different from the linear model. That was a simple model. This is non-linear models. And so a little bit complicated with their initial as given as there. Again, we have used the non-standard funded difference to this complicated model, non-linear model. Again, we describe the system at different nodes and some rewrite the system by transposing the previous point to other sides, and we have to find a solution of this equation. The critical points is again computed here. So we have solved the equation 21, the critical points, equation 22 and 3. We now consider that after solving the situation to 0, we have computed all these 4 points. Although these points are difficult to compute, we have seek the help of some numerical results here. That is, we have system 4 that is the same variance system as 21. Hence, the model 24 has the same critical value, which are equivalent to equation 23 and 24. So numerical result is here. We have seen the T days and PT, the population of diabetes mellitus population, where V1 is basically the infection rate of the first mellitus, and we increase the value from 0.33, 0.43, 0.53. The value of the diabetes population also goes on increasing, and they attain a maximum value. So it means that when we increase the value of without a new one, the population of this diabetic population also goes on increasing. This is a Q2. This is a population of this percentile for complication in the diabetes case. This is the percentile for rate of curing rate eta 2. Let's come to some conclusion part. Mathematical modeling to study the dynamical behavior of cancer treatment cell by using therapies proposed and analyzed. 3 population cells in the classes: healthy, quasi, infected, and fully infected cancer cells are there. The modeling is either 2 stages: without treatment and with treatment. Local and global steroidal model is analyzed, presented in the form of important theorem in the analysis part. Although the X-ray therapy has some side effect on the human body, but still it is better than other treatment. The co-infection model, TB and actually non-linear commodity model is developed. Our study shows that HIV infected patients are at greater risk for a developing cancer of the gastrointestinal tract, although they have some side effect is also to the human bodies. So these are some certain things are there. So Professor Akmal, I have time or hello?
Yes, you have time. Go ahead.
Okay. So actually, my part is basically I have conclusions. This is basically conclusion part is there because I have thought that is the 1 hour time is there. So this is part from my sides. This was my last slide. So if audience can ask me question, but before that, my slide is there. These are some references work. Basically, this is very important slide as a part of me because this presentation is dedicated to Mrs. Antonina and she's a mother of Professor Roxana. She's a was a very great and very nice lady. She has always has a great objective for her life, and with effort she has got all. Her son Lionel and daughter Roxana, they had the privilege to have her lover and protection. I pray that her noble soul may rest in peace wherever she is there, and always bless and shower her blessings on his daughter and his son. So I pray to Almighty that his soul may rest in peace. So I have a big salute, this to great lady, and my condolences and my heartfelt wishes with her. So
thank you very much, Dr. Ramsey. Thank you very much. I know your talk. Okay, we are going to make a question. We have some questions. You can see your message, please. You can see. Es de Juan Carlos Hernández, él es de México. There is a question. You can see the questions, yes. Dr. Ramsey, please.
In the chat.
Message.
Okay, there's a question. I think to organizer conference.
Está agradeciendo a los organizadores por esta invitación. Muy buena presentación. Un interesante tópico. Tiene que dejarnos, dice, pero nos saluda. Ok. Muchas gracias, doctor Juan Carlos. Dr. Juan Carlos is talking to you. Oh, hello, Dr.
Hello.
Yes.
Thank you very much for the invitation. It's a very interesting topic. I have a lot of questions, but I need go to attend another things. I'm sorry. Thank you very much.
Thank you, Dr. Juan Carlos. Yes.
Thank you.
Sí, nosotros, si necesita el correo electrónico, se lo podemos hacer llegar para que pueda hacer las preguntas directas al doctor Ramsey. We are going to...
Sí, muchas gracias. Sí, lo agradecería. Muchas gracias.
Okay, gracias. Dr. Ramsey, I have a question.
Yes.
I think it's the first system where you talk about the X-ray treatment, okay? And you have an SOFT function that is going to be introduced for each kind of cells, healthy cells, cancer cells, and or diminish. No, I think that it's going to affect all kind of cells. But could you tell me this one? Okay, could you tell me which kind of mathematical conditions do you need? Mathematical conditions and for the model condition has ST. It's a global condition. It's some special condition going in the way of the X-ray treatment.
Yes. Basically, the mathematical conditions are there a concern that when we, first of all, we have a very particular condition should be that on the population size, that is A1 at time is equal to 0, when A2 when t is equal to 0, when A3 when t is equal to 0. Initial condition, they are very important. Then we find the condition. For example, I have chosen the delta is a basically signal strength. I have already particular about that. When the signal strength is chosen, there must be some mathematical condition, but the value should be lies between its 0 and 1. The value of delta should be lies between 0 and 1. If the
like a switch function, it's a switch function. That's the right.
Yes, right. So if the value between 0 and 1, it may be that value will be maybe suitable to the strength of the signal on the when we throw the signal strength on the cancer cell. When the population go beyond that 0 and 1 interval, they may cause a harm to the healthy cell also. That is called of side effects. So we have chosen basically, this is basically heavy size functions. Heavy size function, when we have chosen the value 0 and 1, right? Heavy size function takes two values, 0 and 1.
Okay, right? Did you use this function in your simulations?
Yes. We have used this function 0.
But
0 and 1.
0 and 1, no more. But
Yes.
this has to be from time to time. Or X-ray treatment is only one. I don't think so.
Yeah. Actually, basically, this X-ray therapy, basically, it is not a one-time process. It may take a series of treatment, right? Suppose if a person given treatment at particular in one first week, they may be asked to treat at the next month, right? Depending upon the condition of the patient. So it is a series of basically operations that can be performed from time to time. This is not first time.
Okay. Maybe we
When
can
the first time.
Yes, maybe we can think in some delay, no? Do you see? No, some delay in the treatment. ST minus tau from month to month, no? Yes. I'm going to make that. I'm going to explain to people about our question, okay? Bueno, la pregunta mía era acerca de este sistema que está presentando aquí, creo que fue el primero, donde SDT tenía que ver justamente con la mecánica, el factor de mecánica del tratamiento de rayos X, ¿no? Y mi pregunta era cuáles son las condiciones que tenía que ocurrir con SDT. Matemáticamente podemos explicitar mínimamente que sea continua, sin embargo, por el problema en sí o por lo que significa en sí SDT, pregunté qué tipo de función está utilizando y nos indicó que era esa función switch de cambio, ¿no? 0,1, para explicar un poco que no todo el tiempo está con el tratamiento de rayos X, ¿no? Entonces una sugerencia por ahí también podría ir para quienes trabajan en ecuaciones con retardo, que por ejemplo ahí en esa función SDT le pudiéramos colocar un SDT menos tau, donde tau es el tiempo que se toma justamente para ir de una terapia en otra, ¿no? Dr. Ram,
Yes.
The X-ray therapy is going to be for all the rest of the life or only for some time?
Well, it's a very very interesting question. Basically, sometimes when we perform this access therapy to a particular person, first that is taken under the observation, whether it is being suited to him or not. For example, if some kind of complicacy are developed among the patient, then this therapy is not continued, right?
Okay.
So some kind of a person who is going to be under treatment of this kind of therapy, this is put under the observations, right? So they are the constant watch whether the intensity, they are not doing any kind of side effect to the person. If they are the infected cells, they're being eradicated, then they can be further enhanced. And I would like to invite one thing more here. We are also going to working on a model that some delayed model is also there, delayed differential type of model, because in the next we are also performing the delayed type of differential model when we have assumed that when the treatment is delayed to the system, when signal strength is not reached up to a particular time to the patient, what will be as the signal is delayed, right, by some time, then what will be the impact of this model on the patient? What will the condition of patient in that case? This is also a very, because signal strength should be reached at time to a particular point. If it is delayed by something, it may cause harmful to the patient. So that is also interesting things come to mind. So in that we are also developing the model, which we are some delayed type of differential models, right?
Okay.
So
this is going to be our next joint work, Dr. Ramsey.
Yeah, sure.
We have one more question. So first, they say that it's Dr. Ramsey, congratulations for your outstanding presentation. It was inspiring and didactical communication. According to your expertise, what could be some criteria to use continuous, discrete, or computational models in order to study epidemiological disease?
Very interesting question. Who asked this question? It's Pedro Isaac.
Pedro is
part of our group. Yes. Basically, in the beginning, I have I have shown some mathematical technique. If you remember, one second. Yes. If you remember, I have shared these techniques, right? So basically, in this technique, in this model, the differential equation model, in which we use the continuous type of system. In narrow network, we also use some kind of node system or continuous system. But this kind of discrete models and says that your 1 second is that the country what could be the criteria countries. Yes, basically when we talk about the dynamical system, yes, here we have seen that the X-ray studies use here. So this is X-ray, basically time dependent model. This is a continuous type of model. We also use a discrete type of model in the epidemiological model when we have there is some stochastic kind of model is there, right? We do not have any kind of particular information that what kind of system we are dealing with. In sometimes we have deal with a patient. Suppose we want to develop a model on the some cancer model, and we do not have a particular system or particular information about the persons we are going to treat. In that case, we have chosen the particular treatment to a person from time to time, and we then collect the data, or we can collect the information. That is the in kind of discrete types, not continuous type. So that continuous type of discrete type of model, they are helpful. But discrete type of model, they are as far as I consider, and they are not as accurate as compared to continuous model. Continuous model are good model as compared to discrete model, right? Because in the continuous model, when we take the persons who are going to under treatment, we are continuously observation and continuously study that model and continuously applying the intensity to that person. Our computational model in order to study, computational model are really very good model. When we use the work of computers and mathematics, they will also yield a good and also kind of very very noble model and very hybrid type of model is there. For example, I have seen the neural network model, agent-based model, then neurofuzzy models. They're all the computer-based models. With the help of computation and mathematics, we can perform better model as compared to discrete models. Right?
Thank you, Dr. Ramsim. No sé si alguien quiere hacer una pregunta mediante su micro. We are very, very pleased, Dr. Ramsim, to have you in REUMATPERU 2022-2. Es un placer haberlo tenido aquí, Dr. Ramsim. I think that it's not going to be the last time we are going to have you, maybe here in Peru next year, when we are going to make Symbiomat 2023, no 2023, Symbiomat. Sí, desde ya anunciamos que el próximo año estaremos aquí en Perú con la 17 versión del Symbiomat, donde el Dr. Ramsim ya ha participado y seguirá participando junto con nosotros. Le agradecemos a él y le extendemos un aplauso desde acá por su colaboración con no solamente nuestro grupo, sino con todos aquellos interesados, tanto a nivel nacional como internacional, a quienes saludo nuevamente. Dr. Ramsim, here is the people from Mexico, Argentina, Brazil, y Peru, and Peru. Then we are very, very happy to have all these people here in your talk. Thank you for this mention of my mother. It was wonderful. Thank you. I'm going to have here in my heart. Thank you, Dr. Ramsim, and blessed for you also. Muchas gracias a todos, bendiciones para todos, y les anunciamos que la próxima semana estaremos aquí también. Es la próxima semana porque recuerden que hubo una semana intermedia, donde estaremos recibiendo a la doctora Marcela González Araya, ella es de la Universidad de Talca, Chile, con su exposición sobre desarrollo de métodos y modelos de investigación de operaciones para la planificación de cosecha frutícola. Como ustedes saben, estas reuniones son en realidad de todos los alcances de las ciencias matemáticas, y en esta ocasión le corresponde entonces investigación operativa, presentar muy amablemente a nuestra siguiente conferencista, la doctora Marcela. Será viernes 18 de noviembre, de aquí a una semanita nada más ya va a salir el enlace, así que se pueden ir inscribiendo y pasando la voz. Y también a las 10 horas, es decir, a las 10 de la mañana también ella tiene planificado trabajar con nosotros este interesantísimo tema. Agradeciendo a todos, por favor les voy a pedir que prendan su cámara un momentito. Please, Dr. Ramsim, your camera.
Yes.
We are going to...
Yes.
Por favor, todos los que tengan ahí por ahí su cámara prendida. Ahí vemos. ¿Cómo estás, Dolores? ¿Qué tal?
¿Cómo está, doctora?
¿Cómo está, Marta? Marta Nina, ¿cómo está? ¿Qué tal?
Está, doctora, buenos días.
Buenos días, Dolores. ¿Qué tal? ¿Cómo estás?
¿Cómo están?
People from Peru, not only Lima, from north, south, everybody. Some of our students, master students, that maybe they are going to talk with you. Pedro is working, one of the theses is about cancer. Maybe he's going to ask you some questions.
Okay.
Maximo is working in ecology, and then maybe that also is going to ask you. And Javier is a physiology, a physiology model about respiratory system. Then we have all these people working, and we have more people here who is very interested. We have also Lauren working on cancer model. Then everybody is going to ask you. Dolores is working in delay differential equation, and we have more people also working in delay differential equation. Thank you. Wait a minute, please. I don't take the picture. Wait a minute. Okay.
It would be my pleasure to be join your group.
Yes.
Okay.
Okay.
I would like to.
Yes. Okay. We are going. Okay, thank you very much. See you next week, okay? And por favor, pasen la voz para que sus colegas y alumnos también puedan ver estas 3 últimas sesiones que tenemos. Esta es la siguiente semana, pero después de ahí cada 15 días, hasta diciembre, que cierra el papá de Marcela, que es el doctor Eduardo González, quien siempre nos acompaña. ¿Ok? Y la que sigue investigación operativa es en el área de estadística, pero en realidad nos interesa todo. Todo es muy interesante para nosotros escuchar. ¿Ok? Nos vemos entonces. Thank you very much, Dr. Ramsey. See you.
Thank you.
Bye, bye.
Thank you.
Bless you. Bendiciones para todos de parte del Dr. Ramsey.
Thank you very much. See you.
Thank you. See you.